Is that recording?
Yeah.
It says the ultimate old person thing to say. Alright, today... Hello, sorry? I thought you had a question. Alright, today we're looking at where functions meet. And on the screen is, if you have a linear and a quadratic, there are, I guess, three possibilities. Either they can cut with 2 points of intersection, either it can touch at a point, or they won't meet at all. And you could, I'm sure, visualize in your head a similar sort of relationship between two quadratics of two intersections, one intersection, none. So when we graph functions, they won't necessarily meet. Sometimes they'll meet multiple times. And our sort of challenge today is figure out how we solve where they meet. In particular, we're looking at two different functions. X squared take 5x take 6, and minus 5x take 3. And the easiest way to do this is to do it using our graphics calculator, so that's what we're going to start with. Grab your calculators. You can get your calculator. And we're going to graph these functions. Cool, cool. Alright, on your calculator screen, click 5 for graph, and then delete whatever's there. Alright, and then enter in both equations on separate lines. So x squared, take 5x, or take 6, and then negative 5x minus 3. And draw a graph. If your graph looks a bit strange, hit View Window Standard as a good starting point. Or if after you've done that you feel like there's something happening that you can't see, you can adjust your view window. So change your view window so it drops further into negative. So I'm going to make mine go down to neg 15 in the y. And then I have a good idea, I can see the intersection points. Then if we want to find where they meet, press Gsolve intersect. And it will find the first place it meets. And then if you press across, it will find the next place it meets. You can see that the locations they're meeting are not beautiful fractions, so we can't tell exactly. When you reach the next level of nerddom, you'll start recognizing very famous and popular numbers. Does anyone happen to recognize that 1.732?
Is it the square root of 3?
It is the square root of 3. Nerd award, excellent, well done. So, and if it was 1.41 something, it would be the square root of 2. You'll start recognizing common decimals, but yes, that is root 3. Nice, so we're kind of expecting our answer to be positive and negative root 3. But let's say there was a decimal there that we didn't recognize and we weren't able to answer it accurately from the calculator. We have a good decimal approximation. Our next plan is algebraically. So if we're looking at a pair of functions, y equals x squared take 5x plus 6. I lied, take 6. And y equals minus 5x minus 3. So we're looking at these. If we want them to be equal, we can say, well, their y values must be equal. And effectively, it's a set of simultaneous equations. If the y values are equal, it means you can take one y value and replace it with the other y value. So you can take this y value and replace it with minus 5x take 3, because you know when they meet, they'll be the same. So your first line of working here can be minus 5x take 3 equals x squared take 5x take 6. That is where they will meet, or where they meet, that will be true. Then we solve it like an ordinary quadratic style equation, meaning you're throwing everything on one side, getting 0 on the other. So I'm going to plus 3 and add 5x to both sides. Once I've done that, I'll have 0, I'll still have an x squared, and I will have minus 3 on that side. Now, if it was a more complicated quadratic, we could be reaching for the quadratic formula or factorizing or any of our other tools. But as it is, we can solve for that pretty comfortably straight away by adding 3 to both sides and then square rooting. Remember, when we square root, we need to generate that plus minus. And that's what we observed on the graph as positive and negative root 3. Now, strictly speaking, we haven't found the locations they meet. If we were after the locations they meet, what are we still missing?
The y value.
Yeah, the y values. So, the y values here, you can get by substituting the x values in to either equation. So it doesn't matter if you substitute them into this one or this one, because they're meeting at the same point, you should get the same answer. It's a good way to check your answer, is to sub that x value into this and make sure it comes out with the same value. If you're in a hurry and only want to do it once, I would pick the easier one. Our y value would be y equals minus 5 lots of root 3 minus 3, and y equals minus 5 lots of minus root 3 minus 3, which we also write as 5 root 3 take 3. So our 2 points are going to be root 3 minus 5 root 3 take 3, and you can't do much with that. And our second point is minus root 3, 5 root 3 take 3. And it's completely okay for your answer to have a mixture of roots and integers, or rational and irrational. Any sort of question? Yes?
Why does the negatives on the root 5 cancel out?
You mean here?
Yeah.
I guess because here I had positive and negative root 3. If I sub in minus root 3, it reads as minus 5 multiplied by minus root 3. And that minus 5 times minus root 3 ends out with positive 5 root 3. So it's that pair of negatives. And remembering that there's really, between the 5 and the x is a multiply sign. So it's like one negative thing multiplied by the next. I put a dot here because mathematicians get lazy, but really there's a little times in there.
Wait, why is it minus square root of 3?
Because here, when we square rooted both sides, we get x on its own and we get positive negative root 3. As in, if we want to find numbers that we square to get 3, there are 2 possibilities, the positive of root 3 and the negative of root 3. And that's what gives us the pair of points here, positive root 3 and negative root 3. Alright, next question. And this is one where calculator is of limited use. Find the values for A for which there are 2 meeting points. What you're looking at here is this first equation is concave down. It's got a negative in front, so it looks like this. This second equation is concave up. So you've got 2 equations, the first one and then the one with A looks like that. And this plus A on the end has the impact of moving the graph up and down. So this graph here can move down and up, and the question is, what value would A have to be so that it crosses twice? That would have been great to video me stacking on my own power cord. Crosses twice implies 2 meeting points, implies 2 solutions. And we've just studied a tool that lets us find out what values of something would give us 2 solutions, and that's what we're going to apply here. So we're going to aim to find the meeting points by equating the equations or setting them equal to each other, and then we'll go from there. So if we set them equal to each other, minus 2x squared plus 3x take 4 equals x squared take 3x plus a. Now, I want to get everything on one side, 0 on the other. By convention, you want a positive leading coefficient, so it tends to work out better for you if you have a positive number at the start. So I'm going to add 2x squared to both sides and then ditch everything else from this side as well. And I repeat that over there, and what I get is 0 equals 3x squared minus 6x plus a plus 4. Hello, Ms. Travis.
Can I go to R2 for 2 seconds? Is that okay?
You can. From here, we want to know for what values of a does that give us 2 solutions. So, if we're thinking, well, for that to have 2 solutions, its discriminant must be greater than 0. And therefore, b squared take 4ac must be greater than 0. Don't get confused just because a is by default in the discriminant. That a is not the same as this a. This just denotes the places within the quadratic. So this is our a for the purposes of the discriminant, that's our b, and this bit here is our c, and conveniently c contains the letter a. So it's just the fact we've reused or recycled numbers that's not helpful. Recycled letters that's not helpful. Alright, b squared take 4ac is greater than 0. So 36 take 4 lots of 3, lots of a plus 4 is greater than 0. I've done the b squared expansion already. So then 36 take 12a take, it's 12 times 4, 48?
Yeah.
Yeah. So what I've done there is I've multiplied the 3 and the 4 together, and then I've multiplied that into there and there, recognising that it carries the negative in twice.
Is that 12a?
Yes, minus 12a, yep. And then 36 minus 48 is negative 12, so this is negative 12a, negative 12 is greater than 0. And now we solve for a, add 12 to both sides. Divide by negative 12. And note, because we're dividing by a negative, we've got to flip that sign. What this is saying is that if a is less than negative 1, there will be 2 meeting points. A good way to check this is to put in a is equal to negative 1, and that would predict 1 meeting point. And if you put in a equals negative 2, that would predict 2 meeting points. Yes?
Does the bigger than sign only flip when you divide?
Or multiply, as long as it's by a negative.
Oh, okay.
Because multiplying and dividing are effectively the same thing, they just look slightly different. If you're doing it by a negative, then you must flip the sign. Did you guys want to see what the graph of that looks like? We've got minus 2x to the power of 2, plus 3x, take 4, and x to the power of 2, minus 3x plus a. So they don't meet, and certainly if a gets bigger they don't meet, and the prediction we've made is when a hits negative 1, they will meet once. And if a is less than negative 1, they will meet twice. Which is pretty cool. So we can see that as we change a, for values less than minus 1, there will be 2 intersection points using the discriminant. Right. And I think I've shown you enough to let you do 2F, and that's what we'll do for the next half hour or so before we come back for problem solving. Go for it.